Hello everyone, I'm sure you're doing awesome. Welcome to the second part of designing a scalable matrices and the monitoring alerting system like Dynatrace, SignalFX, or New Relic. When we are seeing components like SignalFX, Datadog, or Dynatrace, so they have a lot of unique capabilities and the unique design as we have already covered in our first part of the video. What we have already covered is we tried to design a system which scaled around 100 million daily active users with thousands of server pools, and in each server pool there are thousands of machines, so it goes around like 100k total machines. And the core components that we have discussed so far is we started off with the data collections and how we can transmit the data, and what is the storage engine that goes behind that kind of data which we are going to store, plus all the retention, all the alerting, and all the visualization, all the core components we have discussed. And also we have discussed why we need Kafka in this kind of situation, like Kafka or any kind of message broker sort of a thing, and why not RDBMS, like why we store our cannot use the storage engine of RDBMS, and why a time series database like something like a InfluxDB we can use. Also, some ideas regarding the data modeling, and some idea regarding the batching agents and consumers. The last video again was probably 1 hour long, and a good amount of things were covered there. So what in this particular video we are going to do is we are going to do a very good deep dive around the components. Okay, so when we do deep dive, there are many other nuances around this system will gradually be cleared in our in a conceptual sense. Okay, so how so the first question is like how exactly the database would look like. Okay, so for example in our case, let's start off with database. Like, how would our database that would look like when we are tracking some API requests from like thousands or tens of thousands of backend machines, suppose for the Amazon e-commerce. Okay, this is one of the very measurement that we are getting from our logger job, and suppose it is coming from the logger job in Amazon e-commerce. So if we just see this particular data, what it tells that in this given timestamp, okay, in this given timestamp, the checkout service in the this region, let me just take a pointer. So this is the timestamp. In that particular time, the checkout service, you can see the name of the uh, endpoint, you can say for the time being, in which region it is, in the west region, and for the production from this particular instance ID of 12345, it is taking 245 milliseconds. Okay, so if I again have to repeat, this is just coming from a logger job of a particular API endpoint of named checkout, that from this checkout endpoint of this particular region, the in this given timestamp we are taking 245 milliseconds to return that data. Okay, and what happens is all this data, they will be taken and they will be stored in something called a TSM. TSM is called time structure merge tree. Okay, so this is again a very important term in terms of the understanding TSM. Again, so it is time structure merge tree. So just we are going to see that how exactly the file or the whole file plus the whole metadata looks like for TSM. Okay, so you can see over here the file name, that tsm001.tsm. So it identifies the physical file where the data is being stored, and these files are kind of immutable in nature, and this way, having multiple TSM files allows parallel reads and writes. So there will be so many TSM files or time structured merge tree files like this. Okay, so when we have this particular time range, so that means what is the defined time window for this particular TSM file. Like all the data of this time window is stored in this particular TSM file. Okay, so time series data anyway, they are inherently ordered by time only. So by storing the data in fixed time ranges, system can very easily and quickly locate where a particular given data is. Okay, and there is something called series key. So series key, what it does is it uniquely identifies the data. So you see here for US West, for production, uh, f- the measurement of HTTP request latency, all these data are being stored over here. Okay, so here you see US West, and for another region of US West, we are storing another series key and data. Okay, so all the data that you see over there, this is also very important, it stores the actual time series data. So you can see this is the timestamp, this first part is the timestamp, and this part is the value. So that means in this given timestamp, if you can just tally these two, okay, this one and this one, in this given timestamp, my latency is 245 milliseconds. Okay, now why this format is important? Because these TSM files, they are designed for high write throughput and compression. So in case we are putting the data in this way, so it is easy for compression, and also it is high write throughput. Okay, now this series keys allows filtering of the region, service, and whatnot, and it is very scalable also. Why? Because if you can see here, the next the next place where I'll be storing my time range, it will be just another file. So we do not have to think ki where exactly, like this, having this separate TSM file and the high cardinality, we never have to think like where my next file would fit in. It will anyway keep on expanding into a newer and newer file. Okay, so now that we know that the data are being formed like this, so now let's try to understand how we can use this TSM file to our advantage. Okay, so this TSM files that we have, suppose I have my data of April 1 to April 7th into some TSM files like TSM 1 to 25. Okay, so what I can plan to do is I can plan to store data, only this data to my shard 1. Okay, and similarly from April 8 to um, April 15. So 7 days of data, 7 to 15, or rather 8 to 15. So again 7 days of data, which will be probably from 26 to something like 58. Okay, all of this data I am going to store it to the shard 2. So I can go so on, like just keep on storing the subsequent 7 days range of data into different shards. So generally this is a very popular way to do this, like with each shard will only hold last 7 days data. So what is the advantage that we have with this kind of cases, or this kind of steps? That is, it is being called as retention enforcement, like a background job will keep on checking all the dates, and the target shards, it will keep on entering the data. So we are never keeping more than 7 days of raw data. And so you might be questioning, what do you mean by 7 days of raw data? The thing is that this data lose relevance over the time. Like suppose there is a certain log that you have which is not a problematic at all. Your um, whole database, your whole application is running as smooth as you can imagine. So in that case, do you really go back and check those logs? The answer is no. So rather, what we generally look for is trends, outliers, and those sort of things. So the moment we are doing this sort of architecture, that means like only for the last in a 7 days gap, suppose for last 30 days total data only we are going to store. Okay, and the rest of the data we are going to like in over the time, what we generally do, we generally do a compaction of this data. So what does compaction means? Compaction means we take all those data and kind of merge them. How we merge them, we will come in a while, but just understand this thing. Why we keep the 7 days of we keep this segregation of 7 days of data into the shards? Reason being, these shards do hold only particular TSM files, and that helps in queries. Suppose I want to, as a final user, I want to query data of a given date. Okay, given date, maybe date time minus 1, date time dot now minus 1 or minus 2. That means the day before yesterday, whatever the data was there. So in that case, my query with proper routing would know that, okay, I need to go to this shard X or shard Y, Z, whatever, because I have divided all my 7 days of range into the shards. So it makes the query very easy, and also the disk usage is very predictable. Like we can have this shard one maybe of like 2 TB. In 2 TB, if I can see that all of my 1 week's data is accommodating, then I don't need to really scale it up to some macro instance of 5 TB. Okay, so this kind of advantages we get query, and also can say like this predictable disk usage. Okay, so get all these things, and now let's talk about this part. Okay, let's talk about compaction. Sorry, yeah. So now let's talk about compaction and how does it help uh, this kind of systems. So this compaction is also being called as rollup. To understand this, let's do a simple math. Okay, suppose you have 10K machines in place, and these 10K machines, all of them are sending one request per second. I'm just keeping it very low. They are, of course, more requests per second, but just for the sake of math, imagine it. Okay, so that means there are, like, the system that we are designing, it has 10K points per second. So if I see in terms of a day, it is literally becoming somewhere around 864 million records. Okay, so you can imagine for a system like this, who is having data like uh, all our logging, even clickstream. So clickstream is basically all the places even user is hovering their mouse upon, all the data comes to the server and it gets stored. Okay, so probably you can imagine the kind of pressure the database or the system would be exposed into if we keep on saving all this data, and this data over the time always lose relevance. Like, we generally do not go into a granular log of something that happened more than 30 days. Okay, so for this kind of data, what we do is there is something called downsampling. Okay, so what exactly is downsampling? I will try to explain to you with a sample code. So in InfluxDB, downsampling is being done like something like this. Okay, so after 7 days what we do is we completely take out the raw data. Okay, we probably just need the trend. So after 7 days we only would need the trend. Okay, so what we do is, this is an important part, guys. So here you see there is a given start and end time we have given. It can be a certain time range of last 7 days, or even we can do like a date time -7. And what we keep on doing is, in that time we keep on grouping it by 1 minute, and the service region and environment whatnot. So now, instead of, like, if you see this one, the core component is, instead of 60 points per minute, like the one that we had for each request per second, that means there are 60 data points that are getting created, right? Instead of 60 points per minute, it is becoming 1 point per minute. Okay, so here we can see uh, our data is gradually getting um, compressed or compacted, we can say. So this whole process is being called as compaction plus rollup. So now our rollup window is what? A 1 minute. Now again what would happen is, after 30 days, after 30 days passes by, there is a daily rollup happens. Okay, so after 30 days we can roll up. Instead of 1 minute, what we will do is, we are going to group by the whole day. So now, instead of hourly basis, what we are going to have is, we are going to have a day wise trend. Okay, and that's the secret sauce behind all the graphs that you will see most of the time. After a certain period of time in Dynatrace or in New Relic or in Signal FX, you will see all of them in a day wise. Uh, all of them are in a day wise trend, and the more backward you go, you will see week wise trend or month wise trend, or whatnot. Okay, so in this way, we keep on rolling up of 1 day, 7 day, 30 day monthly for monthly charters. Okay, so in this way, the roll up keep on happening. Now, how all of this comes together? Suppose if I have to do a simple query like this. Okay, so just see, if I have to do a simple query like this, that what exactly happened in my last 1 hour. Okay, this all of these data points are present. So now it will give us the exact latency. This particular query would give us exact latency, like with checkout, with US, in which region, what exactly is the mean latency, and whatnot. So I hope that this part is clear, that what we keep on doing is, because there are such a huge records, and as the data is losing relevance, we keep on storing the trends and the outliers, instead of storing all the data points uniquely. So this process is being called downsampling. And through how do we perform downsampling is, we take the data, we group them by sometimes minute, sometimes by day, or sometimes by week, or even month. Okay, so in this way we keep on doing the roll up. And suppose how our queries look like is, suppose I want to get a service wise grouping of latency, of the mean latency. We just write this sort of query there, and we are going to get our data like this. And again, like if we have to do something for last 30 days, so it will be date time now -30. Okay, so I think again this is pretty much clear. So now let's do a full revision, like whatever the things we have learned so far, and we will try to be a little bit more graphic. So now let's try to visually identify what has happened so far. So there is this data ingestion that starts. So this data ingestion would parse all the data into our into a series sort of a key. Okay, so there is a series key that is being generated, if you remember. So the series key will have things like HTTP request latency, um, HTTP request latency, and then environment, then things like region, and also the service name. Okay, so if you remember, the service name was checkout. I'm not again writing all the things. So here we discuss this thing, right? The service name is checkout and the other stuff. So uh, i- during the data ingestion, what happens is we get this series key. Now this would go to TSM. Okay, so now this would go to our TSM, rather not the TSM file. At first it would go to the TSM storage engine. So what would happen over here is this will make sure that all the time structured merge tree are being the TSM files or the time structure merge tree files are being created. So from here, it will probably get into different of TSM file. So those TSM file will be of a certain time range one, suppose. Okay. So in the similar manner, it will go to TSM file 2, that will be again time range 2, and also there will be another TSM file that is on the time range 3. And all of this will have to go through something called a shard management. So what this shard management layer would do, this shard management will be responsible for taking all the data to the proper shard. So through this shard management, what would happen is this TSM files, they would go to different shards. Suppose here I will just get this one. Suppose this goes to this shard 1, this goes to shard 2, and this goes to shard 3, right? So now we have all the different shards, and it will be very easy to query our database that if I have to get any data of this given time range, I will have here. If I have to do any data within this time range, I will have it here. So now all this data will again come and will go through a a retention check. Okay, so a background job will run of retention check. So this is again important component in all the shards. Background job will run with retention enforcement. And what this retention enforcement will do, this is a very interesting um, this is a very interesting way through which it finds that now this data I need to do a roll up and I need to do a compaction. Okay, so compaction means adding the data and roll up means like grouping the relevant data. So what this job does is this job takes uh, like one of the technique that is uses interesting technique that is called downsampling, and through this downsampling it defines some roll up windows. So the roll up window, it can be like 1 minute, it can be 1 hour, it can be 1 day, or even it can be 1 month. Okay, so there are different roll up keep on happening, and from this roll up what would happen is all this data will be now get into larger complex TSM file. Larger compressed TSM file. Okay. So I hope till this point it is cleared. And then through our user query processing, we can keep on doing like if there is a final user, what they can do is they can keep on doing the they can keep on doing the query. Suppose there is a user, so this user from this larger complex tree, they will be able to query all the data. Okay. So this is pretty much it, guys. Like visually I tried to represent it to you, that how the data ingestion happens, how the uh, storage, the TSM storage engine works, how it comes to different shards, and then through background job and the retention, uh, how the compaction and rollup runs, and then in the larger complex TSM file we can query. So through query we can do a data aggregation, we can do group by or whatnot. Okay. So while discussing the TSM, we anyway on a very high level discussed what is the like how many data points we can actually expect, but in real life it is way more. Okay, so just if I have to discuss about like the Amazon e-commerce, like the Amazon e-commerce data ingestion. So simple thing that would come over here is CPU usage, memory usage, and request count. So if I just compare this three data only, just let's see what goes around. For example, if the CPU usage in every 5 seconds I am getting one data point, for total this 100,000 machines there will be 20,000 data point. For memory usage, suppose in every 10 seconds if I am getting one data point, so for again 100,000 machines it will be 10,000 data points. So similarly for the request counts, if it is coming around 20,000, so per seconds you can imagine it is coming around 50,000 data points, which is actually huge. Okay, so with 50k, with 50k writes per second over 7 days, if I just do the simple math here, it is coming around 30 billion data points. How do we handle it, guys? There is 30 billion data points, and the answer is very simple. We have to do Kafka and plus the time series database, which we already explored. But how do we do it using Kafka? Like whenever there is a very high write throughput is there, of course we have to channel it some way by some sort of a message broker, right? So in our previous video we have seen that all the agents are basically the Kafka producers. Okay, so all the machines like which is emitting the data of CPU usage, if you remember from that previous video, they are basically Kafka producers. Okay, and we are going to have our own consumers. So the key is the scale they write to each, they write each data in each portions in Kafka. So when I say portion means in the Kafka there is something called topic is there. So we have already discussed in another system design video of us, like what is the topics in Kafka. So topics in Kafka is something like within Kafka only different pipelines we can use. So this is going to be one topic. Okay, this is going to be one topic, this is going to be one topic, and this is going to be another topic. So what we have is we write our data into different topics in Kafka. So here, if this is Kafka, if this is my message broker of Kafka, this has three topic right now, one for memory usage, one for the matrices. Sorry, this is not memory usage, I will mark it as CPU usage. This is for matrices memory and this is for the request details. Okay, so all of this data, as you can see, this 20k data will be coming here. For the matrices, around 10k data will be coming here. For CPU usage, again around 20k data will be coming here. So they will not overlap with each other, they will be in separate topics. Now in my previous on the first part I got a comment that why do we need separate topics. Okay, so let's say the CPU usage suddenly spikes globally. Like here I was having 20k and suddenly it goes like 150k. Okay, for some strange reason uh, my server maybe it is getting some kind of a attacks or some other very high computing processing is happening. So from 20k it goes around 150k. Okay, so what would happen in this case? In this case, this is almost a 7x surge is happening. Like only for this one there is a 7x surge is happening. Now just imagine if all of them were, instead of separate topic, in a single pipeline they all were going through. So memory and the request, this matrices memory and the request data, now in this case they are not getting affected, but had it been a single one it would definitely would have been affected, right? So consumers will also get into the problems if we do not have separate topics. Consumer had to process everything together, and suppose there is a certain consumer which is preparing the report for CPU usage, how difficult it would be for it to just only pick the data of CPU usage, because it is having a galore of data, right? So why separate topics? The first thing is to make it more resilient. Okay, and the second thing is to make it consumer friendly, so that we can write separate consumer for separate topics. So again, with this separate topics, if I have to revise that CPU, in case the CPU get overwhelmed, we only have to scale the CPU consumers or the CPU topic related components. Okay, so no cross matrices, no cross matrices interference is happening over here. And in real world, even if you see, Netflix uses separate streams for traces, matrices, and logs and whatnot. It is completely the same principles that what we are discussing over here. Now, if we have to take a step back, why this message broker like Kafka in the first place? Can't we send the data directly? So this question also might be coming to your mind. But let's take a scenario, something like Black Friday. Okay, so suppose in a Black Friday sale has started in your e-commerce app, and the traffic definitely surges. Okay, so the CPU sampling increases on every single seconds. So now we are probably having like 100k per second for just for CPU. Okay, so Kafka in this kind of cases work as a circuit breaker. How? Producers, like this is the role of the producers as well. So basically machines are generating these results, right? Like if I see this, if there is a machine, if there is a server, this server is basically generating all the data, right? So now what would happen is server generally before sending those data, they batch it, and you can understand like maybe it batches the 5 seconds of data and send it, or in 2 seconds of data it sends like a 2 seconds batch. Now if the it it becomes really heavy in terms of the payload, then how come our consumer will be able to consume it so fast? So Kafka work as a spike absorber. That is a correct term I can come up with. Like it works as a spike absorber, because it take all those spikes, or suppose it doesn't really matter whether the batch size is absorber, yeah, right. So it doesn't really matter if the batch size is 100 MB or 2 MB in size. It it maintains the constant data stream. So that is why this message broker is important. And also, if you see historically why Kafka was first came in use, LinkedIn made it. Okay, so it's a very interesting story behind Kafka. So they were unable to handle this same scenario. That's why they came up with Kafka, and they were able to handle every single thing. So message broker was a that is the first time message broker was used in that huge scale. So yeah, now I think it is clear to you that how exactly ingestion works. So ingestion works through a message broker, and within that, it doesn't really matter how many new data points that we are sending. We segregate those data points, and we maintain a flow of data stream by using Kafka. And now the advantages, the consumers, like whoever is reading those data, suppose there is a consumer, this all these consumers are there. Okay, suppose, so these consumers will have a steady data streams. This worker processes, they will read from Kafka, and further what they will do is they will write data to our time series database. So all the TSM files that we were talking about, so from here the data would go to our database as a TSM files. Okay, so this is the whole flow that I wanted to discuss for the as a part of our data flow. Okay, and as a part of our ingestion process. So now we will just try to understand why this is super scalable, and then we will be able to appreciate that how beautiful this design is overall. So suppose your customer like Amazon e-commerce, it asks for a new matrices. It tells that I'm going to need a new matrices, and the matrix that I need is latency per request. So latency means like how much time it is actually taking from uh, c- starting from the server to the client. So those latency details I'm going to need as well. Okay, so what we are going to do is those for fetching those records, of course, we need to configure our agents. So once we configure our agents, we are going to emit that data. So you see this particular measurements and this particular tags, like for checkout service, and in the region US West, what is the latency I am getting on a given timestamp. Okay, I am going to emit the data, and then just concentrate on this part. We are just going to create a new topic in Kafka. So earlier we had CPU usage, matrices of memory, and the request details. So now we are going to have the matrices of latency. That's all, nothing else. So this particular this particular server machines or our agents, whatever the data that it will be emitting, it will be emitting this request latency data. And for that request latency, plus what we are going to have is we are going to have a new consumer as well. So if you see, now we are going to have a new topic as well, and that topic would be going to a new consumer as well. That's all. So no other change, nothing. And if you see in this whole process, our database, our whole data ingestion remains as it is. We are not going to make any given changes into that. So just a change in the agent to emit the data, and adding a new Kafka topic, and configuring our consumer. So in the end, how this whole architecture looks like, and we are just going to conclude with this. So suppose there are 100k machines are emitting the data, and from those machines, using those agents, we are going to emit the actual data. It will come to the different Kafka topics. All these things that you see, they are different Kafka topics, and for each topics we are going to have a consumer or a consumer group. So consumer group is again for resiliency, that if you have a group of machines, then there is a less chance of outage, right? And then they are going to write the data to the InfluxDB. One of the important aspect is, after we get the data into the InfluxDB, although we can query our data, but generally these systems, they have their own visualization dashboards. For example, Dynatrace, it has its own visualization dashboard. If you are using your completely a custom made monitoring tools, then you can use Grafana. So using Grafana, you can create your own domain also and deploy your Grafana there. Okay, so that is what the visualization is, and it is one of the, probably for the end user, this is one of the most important component. For the developers, definitely the querying capabilities of InfluxDB and other things are important, but for the business perspective, if you see, like the people who takes the decision, for them, this Grafana is a very important thing. And these days, if you see across SREs or the platform engineers, everybody is using Grafana. Okay, and another important part is the alerts. So what exactly our alerts are? Suppose there is a certain matrices. Suppose my CPU usage is above and beyond 90% for last 2 minutes. That is definitely a very big concern, right? So for that, we had built-in alert manager. For example, InfluxDB has something called InfluxDB alert, which is being written on top of Flux queries. Okay, so it can trigger thresholds or anomalies or even some rules. Okay, there can be like composite rules, that if my CPU usage is this and if my latency is xyz whatever, then escalate it to my monitored mailbox, and there will be a email that will be triggered to hierarchically to multiple people, like starting from SRE to platform engineers to developers, to fix that. So yeah, this is pretty much it, guys. This is how we are going to do the visualization, and this is how we are going to do the alerting. So I hope this part helps, and this concludes our deep dive into the scalable monitoring system. See you in my next video. Thank you so much.